All right, good morning, ladies and gentlemen, and might I say, the panic is real. Um, so this mock exam 3 has really gotten people very worried. I just want to tell you that these two questions are much, much longer than anything you should expect to see on the actual AP exam. That being said, these two questions really go into a lot of the more challenging concepts, and so I really think they're a great couple of questions. In fact, I think they're so good that I'm going to take time to go over each question on separate videos, and I want to talk about even each part of each question. So they might be a little bit longer videos, but I really think that by test day, if you understand all parts of these two problems after this video, and maybe after you kind of think about it on your own for a little bit longer, then I think I think you're in pretty good shape. All right. I'm not saying if you just understand how to solve these particular problems. I'm talking about if you understand the concepts in these problems, because it is these concepts that that might be like the very challenging part of the AP exam. So anyway, let's get into it. We'll start with question 1. Here's your host. This is me, Mr. G. So we have a student who understands this fact that the letter E appears in 11% of all words. And then this student is actually curious about one of their own textbooks. All right, so this student takes a random sample of 200 words from one of his history textbooks. And so the rest of these questions basically discuss the possibilities or basically the statistical studies around, the number of words that contain the letter E within this one single history textbook. So basically, the population that we're interested in is the words is all words in this history textbook. And so within this history textbook, there lives, let's say, a whole bunch of words like the, words like, this is a history textbook, so probably the word war, or the word couch. Oops, that's CH. Or the word potato famine, so on and so forth. So a whole bunch of words live within this textbook, and we're trying to analyze these words within this textbook. So he goes in, he dives in, he takes a random sample of 200 words, and 30 out of those 200 words contain the letter E. We call that P hat, right? Because we're counting a proportion. Out of the 200 words, 30 of them can fit into the category of containing the letter E, right? So right off the bat, some things should be, you should notice some things that we're talking about qualitative data here. And what we just did is we discovered a sample proportion. Now, part A, name the procedure that the student could use to examine if his entire history textbook is different than the reported proportion. So basically, this student is going to study. Let's define our parameter first. You don't necessarily need to do this to answer this question. I'm just trying to give you a little bit extra detail so you really fully understand what's going on and like how it connects to everything we learned throughout the year. So the parameter of interest is the true proportion of words with the letter E in this textbook. And we're interested, is this textbook different from what was already stated, which is 11%. So we're going to assume that the textbook is the same, that the true proportion in the, of words with E in this textbook is equal to 0.11. The alternative hypothesis is going to be not equal to, because for this textbook to be different, it could either have more than 11% or fewer than or less than 11% words with the letter E. All right. So what procedure would we use to make a decision on these hypotheses? This would be a it would be a two-tailed test, yes, but it would be a one proportion Z test. Okay. So that's part A, one proportion Z test. Oh, part B, write the appropriate hypotheses that would be used to carry out this procedure. We already did that. It would, H null would be that P equals 0.11 and HA equals, P is not equal to 0.11. Part C, if the 11% proportion was exactly true for this random sample of 200 words, you would expect there would be, you would expect there to be 22 words with the letter E and 178 words without. Describe why these values are important and what condition they verify for this procedure. So this is referring to the success failure condition. So basically, if we really want to go ahead and analyze and try to study these hypotheses, so here's part C. We want to make sure that P hat is distributed normally with a center of 0.11 and a standard error of 0.11 times 0.89 over n, which is 200. All right, we need to make sure that this is true in order for us to really go ahead and find a p-value. Now, in order to do that, certain conditions have to be met. The condition that they're referring to here is the success failure condition, okay? It is not enough just to say, oh, this checks the success failure condition. What does that mean? Like, why is the success failure condition important? So let me, I'm gonna just adjust my screen so I can write a little bit neater. Give me one moment. Okay, so for part C, again, we're trying to see, is this true? Is our sampling distribution normal with the center of 0.11 and a standard error of what we see here? Well, one of the aspects, of course, one of the very important aspects, of course, is the shape. And in order to determine that the normal shape is appropriate, we have to check the success failure condition. And so that's what part C is referring to. So you might say something like, describe why these values are important. These values are important because they are referring the number of successes and the number of failures. We need these numbers to be both greater than 10 so we can apply the normal model to our sampling distribution of sample proportions of words with the letter E. Just to add a little context there, of course. Now, if you didn't watch my video on the conditions for sampling distributions of sample proportions, I really strongly recommend that you do. You'll see exactly why this condition, the success failure condition, helps us guarantee a normal model. Please watch that video and also do the same for the conditions for the normal, for the sampling distribution of sample means. All right, one moment. All right, welcome back. By the way, I realize I misspelled the word referring, probably other words as well. So part D tells you that the p-value was calculated to be 0.071. Write the appropriate conclusion for this procedure using alpha of 0.05. Also interpret the p-value in context. All right, a lot going on here. So let's just be clear about exactly how this p-value was calculated, because it will come in handy when we get to the part I and part J problems that a lot of people were very, very, very unsure about. So basically, if the conditions are met, as I mentioned before, then we know how p-hats are distributed normally, okay, with the specific parameters. In this case, the center of the distribution of p-hats is 0.11. That's our null hypothesized assumption. These are, again, this is just the distribution of p-hats. Remember that our observed p-hat, in other words, our point estimate or our sample statistic, whatever you want to call it, that was 30 over 200. And this gives us 15%. So I'll just write it as 0.15. Right, so that's our observed stat. Now, to calculate the p-value in a two-tailed test, we ask ourselves, what's the probability of obtaining a p-hat of greater than 0.15? Right, so we're shading this portion of the sampling distribution, or the probability of obtaining a p-hat as extreme in the other direction. And so if we want to go as extreme in the other direction, we're going to go 0.04 to the left, which would bring us to 0.07. And we're being told that this number is 0.071. And this is your p-value. All right, so just look at exactly how we calculated this p-value, because this will help in part I. We found the proportion of values that are below 0.07. In other words, if H null is true, the proportion of p-hats that would be below 0.07 plus the proportion of p-hats that would be above 0.15. And that total area is 0.071. By the way, my shading is definitely not to scale, and that shading should be perfectly symmetric, which you can see it is not in this case. But forgive me, I am no artist. Now, how do we interpret this p-value? Here we go. It's definitely something that is likely to come up on the AP exam, interpret a p-value. So we start out with saying, essentially, if H null is true. but we of course need to say that in context. So if the true proportion of words with the letter E in this textbook is 0.11, in other words, if H null is true, then the probability of observing a sample proportion of 0.15 or more extreme in either direction. So that, or more extreme in either direction, I'm saying those words because we're doing a two-tailed test. If this were, let's say, just an upper tail test, I would simply say 0.15 or greater, okay? So the probability of observing a sample proportion of 0.15 or more extreme in either direction is 0.071, okay? That is the interpretation of the p-value. Did they ask us to make a decision? Oh yeah, so, and we also have to write an appropriate conclusion for the hypotheses. So this is my interpretation of P. The decision that I would make is the following. Since 0.071 is greater than our alpha value of 0.05, we would fail to reject H null. In other words, we've obtained a sample that doesn't seem that crazy. There's about a 7% chance of seeing a sample like this if H null is true. And that's kind of rare, but it's not crazy rare. It does not go beyond our threshold of 5%, and therefore we're going to fail to reject H null. Therefore, there is not evidence to support the claim that this textbook has a different proportion of E's. All right, and there you go. So on the left side of this current screen, you see exactly how the p-value is calculated and you see its interpretation. And on the right side of the screen, you see the decision that you would make about the null hypothesis and then a statement about the alternative hypothesis within the context of this situation. All right. We're not even halfway there, or we're getting close to halfway there. So like I said, this is a crazy long problem. Please don't expect to see something like this. All right, part E. If an error was made in this procedure, would it have been type 1 or type 2 error? Describe a consequence of this error. All right, let's find an empty spot. I know I'm all over the place. So just a little reminder about errors. So in the world of hypothesis tests, there's the truth. So either H null is true or H null, or H null is false. All right. And unfortunately, we really never know the truth. But just let it be known that those are the only two actual possibilities that could exist in the real world at any, let's say, one time. And then, of course, on our end, what we do in practice is we make a decision. We either reject H null or we fail to reject H null. Let's call this our decision. Right, and so if H null is true and we reject H null, this is called the type 1 error. If H null is false and we reject H null, this is not an error. In fact, this is a significant result. If H null is true and we fail to reject H null, then that's just a correct result. It doesn't have a special name or anything like significant result. And finally, if H null is false and we fail to reject H null, this is called a type 2 error. So in this particular problem, what type of error could we have made? Well, what decision did we make? Back over here, we failed to reject the null hypothesis. So the only possible error that we could be making is in this bottom row here, which is a type 2 error. So we would say if we made an error, it would be a type 2 error. Then the question goes on to ask for a possible implication. I don't know if there would be really any serious implications, but the implication would be, so this would mean that our book, or that the student's textbook, actually has a different proportion of ease, or really different proportion of words with ease. And we don't think that it does. I don't know if there's really any serious implication of that. I'm actually curious to see what the solution set says. So give me one moment. I'm going to check it out. Yeah, so the solution says that we've concluded that this book is not different from others when in fact it is. So, okay, that's one thing where we're going along the wrong assumption that this book is not different than others. Okay, not really a world-breaking implication, but that's the implication nonetheless. But I understand where this question is going, because typically when we do decide on what error we have, a typical follow-up question is, well, what are the implications of that error if you did make that error? All right, so that's part E. Now we get into the fun stage where we talk about the simulation. All right, I want to make sure that we all understand exactly what we're looking at when we look at this simulation. So give me a moment. I'm actually gonna make a few copies of this dot plot so that I can draw over it a number of times. So one moment. All right, so what are we looking at here? So basically, this student now was given access to some software, and he told the computer, hey, computer, the probability of success is 0.11. What I want you to do is dive into this population of words, pull out 200 random words, and give me the proportion of those words that contain the letter A. For example, let's say this sample that he went out and actually chose from his book, let's say that this was one of the samples that the computer went out and got. Notice that the number of E's out of 200 words that were selected was 30. And so this single sample would be one dot on this dot plot. Okay, so that would be the result of one simulation. But then this person told the computer to do the same thing 100 times total. So basically what the computer is doing is it's diving into this population and it's pulling out random sample, random sample, random sample, random sample, random sample. And it's doing that a total of 100 times. For each time, it's counting the number of words that contain the letter E out of 200. And for each time, it's placing a dot on this dot plot. All right, so out of the 100 samples, there was one sample that had 10 words. I think this is probably around 10, that had 10 words, exactly 10 words out of 200 with the letter E. There were 3 samples that had 15 words out of 200 with the letter E. There were 1, 2, 3, 4, 5 of these samples contained 20 words with the letter E out of 200, so on and so forth. So what you're looking at, each of these individual dots is one sample proportion, really. And so let's think about this. These are all sample proportions. This is a distribution of sample proportions. This is the distribution of p hat, or at least it's a part of the distribution of p hat. It's an incomplete distribution of p hat, because as we know, if we were to find all the possible p hats from this sample, it's funny, this kind of looks like a bug or something right now, but if we were to find all the p hats that we possibly could from this population, well, we know that our p hats would be distributed normally with a center of 0.11 based on the null hypothesized assumption, and a standard error of what we see here. What you're looking at here is a partial construction of that sampling distribution. We haven't quite got the entire shape down. We haven't quite, there are some gaps here that if we let this simulation run infinitely, those gaps would be filled out, and we'd ultimately get a shape that kind of looks something like this, right? Something that's nearly normal, that's centered at 0.11 or 22 out of 200, and with the standard error, again, that we saw there, all right? So I just really wanted, this is the important part, that you understand what this, this dot plot is showing you. It's showing you a partial construction of the sampling distribution. All right, I'm not going to go into part F, describe the distribution. Again, center, shape, spread, unusual features. Yes, I think it's okay if you describe this as slightly skewed right. Totally think that's fine. I wouldn't say that it's bimodal though. Because I think for bimodal, there needs to be 2 very distinct peaks. And I don't necessarily, I don't agree that I see that there are 2 distinct peaks. All right, so I'm skipping F because we've seen that so many times. G, without performing calculations. All right, so this basically, part G, you would answer depending on how you answered part F. If you said that this distribution of sample proportions is slightly skewed right, then the mean would be greater than the median, right? Because the median is a resistant measure, and it would not be attracted to the tail like the mean is. However, if you said that this distribution of sample proportions is nearly symmetric, then you'd say that the mean and the median are approximately the same. All right. Is it appropriate to say that this simulation is simulated as a binomial distribution? Why or why not? So I think besides the fact that we are taking our numbers and we're dividing by 200, which creates a proportion. I do think that ultimately, and just like anytime we are analyzing sample proportions, we are starting off with a binomial study, and then we are dividing by the number of values in a sample size to get a proportion. Notice that for each word that we chose from a sample, each word was either in the category that it contained an E or it did not contain an E. And so that meets the one criteria for binomial distribution, in that each outcome is either a success or a failure. Right? In this case, it would be a success if it contains the letter E, because that's what we're keeping track of. That's what we're counting. It would be a failure if it does not contain the letter E. Each selection, each word that we select is an independent selection. So the probability of success does not change. Why? Because there's a massive population of words. And look at any of your textbooks. We have a ton of words. And so when we choose just even 200 words out of this population, we are not drastically affecting the probability of any next selection. So we have independent trials, and also we have a fixed number of trials. Every time we dive into this population and draw a sample, we are only drawing 200 words. So there is a fixed number of trials that we're dealing with. So yes, I think you would be able to think of this as a binomial distribution. Part I, this is the one that gave students a lot of trouble. And I want to say that they mentioned Part D for a reason. Let's go back and see how we calculated the p-value. For the p-value in Part D, we asked ourselves, what is the probability that p hat is greater than 0.15, or the probability that p hat is less than 0.07? Right? And when we had our normal distribution, it was pretty easy to do that. You can use normal CDF. But with our simulation, we don't have the complete sampling distribution. So we have to use what we have. Okay. So again, that p-value was, let's write it down over here. Part I. The p-value said, actually, let me copy it and paste it over here. Give me one moment. All right, and we're back. So again, this was the p-value based on the actual sampling distribution, but how do we calculate this p-value using the partial sampling distribution that we have up here? Well, let's go ahead and calculate these exact same probabilities, but using the dots that we have. So the probability that p hat is greater than 0.15. Well, 0.15 corresponds to 30 out of 200. So we want to know what's the probability of getting greater than, it's actually technically greater than or equal to. So we want 0.15 or greater. And that is 1, 2, 3, 4, 5, 6, 7 dots out of a total of 100, right? We ran this simulation 100 times. There were 100 dots here. So we have 7 out of 100 plus 0.07 or fewer. 0.07 corresponds to 14 over 200. So that would be, just to the left of this 15. So we have 0.07 or fewer. And notice that there's only one dot here. So only 1 out of the 200 corresponds to being 0.07, a p hat of 0.07 or fewer. And this, of course, gives us an 8 over 100. And since this is only a partial construction of the entire sampling distribution, this is just an approximation of p-value. Right, and so you can see that the results of the simulation are fairly close to what we would expect if we were to assume that the that the probability of success is 0.11. All right, now part J. Actually, not finished with part I. How do the results in the simulation compare to the... Okay, so I would just say that the results in the simulation are pretty close to the actual p-value. And I guess the explanation is just kind of showing the calculation that I'm showing you here, the 7/100 plus the 1/100. All right, part J. Based on this, the results of the simulation, how many words would you need to see in a sample of 200 with the letter E to convince you that the book has fewer words with the letter E than the 11% that is claimed? Now, this is kind of an annoying question because of the slight change in wording means we're actually setting up a new set of hypotheses, right? We're testing to see that our book actually now has fewer words with the letter E than the 11% that is claimed. So if we think of this in terms of a hypothesis test, we're assuming, again, that P is equal to 0.11. But if now we're testing to see that there are fewer words than what we hypothesize, we would have our alternative hypothesis be less than 0.11. A standard alpha is equal to 0.05. Now, in order to be convinced that our book has fewer words than the letter E, that means we need to reject H null, and we need to have some sort of evidence that the alternative hypothesis is true. Well, when do we reject H null? We reject H null when the p-value is less than alpha. So we need to find the value that, based on the simulation, would give us a p-value that is less than 0.05. Well, let's see what that value is. Where did I put the other one? Ah, okay. So again, there are 100 dots here, and we want the value that gives us, the p-value that we would calculate is the probability that p hat is less than some number. So we would go in and we would observe some p hat. We want that probability, we want this number, this probability, to be less than 0.05. Well, let's say we just chose 16. And we said, oops, let's say we replace this question mark with 16/200. Well, what's the probability based on this simulation that p hat is less than 16/200? That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And by the way, this should be less than or equal to. So that would be actually 10/100, which is 10%. So that value wouldn't do it. Okay, let's try 15. And I think you can clearly see that 15 is going to do the trick. So if we set our threshold to be this number 15/200, then we only get a 4% probability, or a 4% p-value that is less than our alpha value. Therefore, we would reject H null, and we would support our alternative hypothesis. So that's exactly what is going on there with this question. A complicated concept, parts I and J, both of them pretty complicated, but I want you to really sit and think about what I just said, really sit and think about these problems for a little while to make sure you completely understand exactly what this simulation is showing and how it applies to those questions, parts I and J. As far as part K, I'm not going to go into the details, but basically you would use this. Remember, this is a partial construction of the sampling distribution of p hats. And so what you would do is just find the Q1 based on this dot plot, find Q3 based on this dot plot, subtract those two numbers in order to get the IQR of the distribution of p hats. All right, folks, I know that was a long video, and expect another long video for the second problem. Again, don't worry, the actual problems that you face on the AP will not be this long and will likely not be this complicated. This just happened to be a very complicated, very wordy problem. So if you can get through this relatively unscathed, you'll be in pretty good shape for the AP exam. Either way, I think, ladies and gentlemen, if you're working hard, you're going to do okay. So don't panic. All right, I'll be back soon with another video.